Hey, welcome. Today we're going to be detectives. We're going to unravel a mathematical rule you were taught to obey, but probably never told why. It's a rule that seems simple, but when we really dig into it, it opens up a door to one of the most powerful and beautiful ideas in all of mathematics.
So, let's start with the central mystery. What is 1 divided by 0? You learned in school that it's forbidden, right? You were just told you can't do that, and that was pretty much the end of the conversation. But that's not a very satisfying answer, is it? It doesn't explain anything.
You know, when you ask people this question, you usually get one of two answers. Some people get this intuition that if you divide a number by something that's getting smaller and smaller, the answer must be getting bigger and bigger. So, infinity, right? Makes sense. Then you have the other camp, the people who just remember the rule from their math class. It's not allowed. The answer is simply undefined. But why? What is it about this one operation that just breaks math?
Okay, so here's our game plan for this little detective journey. First, we'll look at what we'll call the zero problem in basic arithmetic. Then, we'll rewrite the rules to see exactly where things fall apart. After that, we'll get infinitely close to zero using a cool tool from calculus, which leads us to a tale of two infinities. And finally, we'll ask the big question, what is infinity anyway? The answer, I promise you, is probably not what you think it is.
First up, the zero problem. To really get to the bottom of this, we have to stop thinking of don't divide by 0 as just some arbitrary rule we have to memorize. No, we need to treat it like a real mystery that actually has a logical, and I think, a surprisingly elegant solution. All right, on to section 2, rewriting the rules. Now, to crack this case, we have to look at division in a completely new way. We can solve this whole thing just by thinking about the fundamental relationship between division and its total opposite, multiplication. See, any division problem can be flipped around and rewritten as a multiplication problem. They're two sides of the same coin. For instance, we all know that 10 divided by 2 is 5. And that's true because 5 times 2 equals 10. See, those two statements are just different ways of expressing the exact same fact. This inverse relationship, this is our first huge clue.
So, let's apply that exact same logic to our mystery here. We're trying to figure out 1 divided by 0. Let's say the answer is some unknown number. We'll just call it question mark for now.
Using our inverse rule, we can just flip the problem around. 1 divided by 0 equals question mark is the exact same thing as saying question mark times 0 equals 1. And now the problem looks very different, doesn't it? The contradiction is starting to stare us right in the face. Okay, so think about it. What number can you possibly multiply by 0 to get 1? The answer is nothing. There isn't one. There is no number anywhere in the universe that can do that. We know that anything times 0 is just 0. You can't multiply something by 0 and magically get 1. It is a complete logical impossibility. And that's why in the world of basic arithmetic, the case is closed. We call it undefined because it just doesn't make any sense.
But wait, the story does not end there. Not even close. This is where calculus waltzes in and gives us a much more satisfying, much richer answer. So let's change our approach. Instead of trying to land exactly on 0, what if we just get infinitely, ridiculously close to it? This, my friends, is the powerful idea of a limit. To explore this, we're going to use a tool called a rational function. Let's look at the classic example, the function f of x equals 1 over x. Now, by its very definition, these functions explicitly forbid the denominator from being 0. But we can still use this function to see what happens as we get incredibly, incredibly close.
So let's just plug in some numbers for x. We'll start from the positive side and get closer and closer to 0. If x is 1, 1 over x is 1. Simple enough. If x is 0.1, the answer is 10. If x is 0.01, it's 100, then 1,000, then 10,000. You see the pattern, right? As our input x gets tinier and tinier, the output just absolutely explodes. It's shooting upwards. It really looks like it's heading towards infinity.
And this leads us to the climax of our investigation. I call it a tale of two infinities. That idea that the answer might be infinity seems pretty solid so far, right? But we've only looked at the problem from one side. The final clue, the one that solves the whole mystery, requires us to approach 0 from both directions.
So, we just saw what happens when we sneak up on 0 from the right, using positive numbers like 0.1, 0.01, and so on. The function just rockets off to positive infinity. But what happens if we come at it from the left?
using negative numbers like negative 0.1 or negative 0.1. Well, 1 divided by negative 0.1 is negative 10. 1 divided by negative 0.01 is negative 100. The function is plunging downwards, heading straight for negative infinity.
This graph of 1 over x shows the problem perfectly. It's the smoking gun. On the right side, as you get closer to 0, the curve goes up forever. On the left side, it goes down forever. And here is the absolute key to everything. For a limit to exist in calculus, you have to be approaching the exact same value from both directions.
And here, we clearly aren't. From one side, we're speeding towards positive infinity. From the other, we're hurtling towards negative infinity. Since we are getting two completely different results depending on which way we approach, we have to conclude that there is no single, coherent, defined limit at 0. This is it. This is the definitive calculus reason why the answer must be undefined.
You know, this whole investigation helps us understand something really profound about the idea of infinity itself. So what is infinity? We can finally talk about what it really means in math, and it's almost certainly not what you think. It's not a number. It's not a place. As this quote from the OpenStax calculus textbook puts it so well, infinity is not a real number like 5 or negative 10. It is a symbol. It's a concept we use to talk about a process that never, ever ends. It's the idea of endlessness itself.
Think about it this way. Infinity describes the journey, not the destination. It's like pointing down a road that goes on forever and saying, it's that way. It tells us that a function's values are growing without any bound, without ever stopping. It describes where the function is going, but it's not an actual place it can ever arrive at. And that's why infinity can be part of the description of what's happening, but it can't be the final numerical answer to a problem like 1 divided by 0.
So, let's close the case. Here's the final report. From a pure arithmetic, logical standpoint, trying to divide by 0 creates an unsolvable contradiction. And from a calculus standpoint, trying to find a limit as we approach 0 sends us in two completely opposite directions at the same time. This rule against dividing by 0 isn't just some arbitrary thing your teacher made you memorize. It's a fundamental consequence of keeping math logical and consistent.
Ultimately, this whole journey shows us that, sometimes, the most fascinating parts of math aren't the simple answers, but the questions we find when the rules seem to break. Asking why can't we divide by 0 doesn't just give us the boring answer undefined. It actually cracks open the door to the entire, beautiful concept of limits, which is a cornerstone of all of calculus. And it makes you wonder, doesn't it? What other simple rules are out there that are actually gateways to a much deeper, more interesting universe of ideas?